Hi HMS modelers, this is Matt Fleming. I work at the Hydrologic Engineering Center, and in this video I'm going to talk about modeling Baseflow using HEC-HMS. On this slide we have a figure that shows just a typical runoff hydrograph, and for that typical runoff hydrograph I've broken it up into multiple components. So we have the direct runoff component, the interflow component, and baseflow component. And we see that the direct runoff component, that's the component that really contributes to the flood magnitude. The base flow component, so interflow and base flow, those are important too. They do contribute somewhat to the peak flow, but they're mostly going to contribute to the total runoff volume. So if you're looking at problems that consider volume, so maybe sizing some kind of detention structure, or you're looking at duration of flow above some threshold, then that volume or that base flow is an important consideration. We see right here, base flow is comprised of runoff that infiltrates into the ground, then it flows down gradient or down slope, and then it reaches back in or flows back into channels. And so it might flow back into a smaller channel, and then that channel becomes a larger channel in a stream and a river, and then so on. Base flow includes multiple components, so we have an interflow component and what we also refer to, or what I'm going to refer to as a base flow component. So either I'm going to call it base flow, and when I do, sometimes I'm going to mean interflow and base flow, and other times I'm going to mean just base flow, which when I talk about that, that's saturated groundwater flow, so we have water that percolates into the groundwater table, and then water from the groundwater table does contribute to channel flow at some portions. Interflow, that's going to be water that travels in the unsaturated portion of the soil down gradient, and then at some point it's going to come back onto the land surface in a small stream or channel. There's different methods for modeling base flow. You have conceptual methods and then process-based methods, or also physically based methods. In HMS, HMS only includes conceptual based methods for now. In the future, we hope to add some physically based methods, but currently as of HMS 4.7, you can only use or choose among different conceptual methods. And as you can see on this slide, there's different approaches or methods for identifying portions of the base flow contribution to a hydrograph. And so on this figure here, I've identified the point of inflection. And so what the point of inflection refers to is it's when the recession point of a baseflow hydrograph, when that curve transitions from a concave downward facing curve to a concave upward facing curve. So that point of inflection, it usually indicates when you have a different source or a different major contributor to the runoff hydrograph. In this case, we're going to say, well, at that point of inflection, that's where base flow, which is going to be made up of both interflow and groundwater flow, are the major contributors to the runoff hydrograph. You can plot your runoff hydrograph in log space. That's what I've done on this figure right here. And you notice that the recession limb is going to look different. So if I go back to the previous slide, you see this nice curve right here for the recession limb. So for the same hydrograph, if I plotted that using a log axis right here, you can see that that curve transitions to basically straight lines along the recession limb. And when you look at it that way, it's a little bit easier to point out, well, for this portion of the curve with this consistent rate of recession, that's going to be my interflow portion of the runoff hydrograph. For this curve right here, where the change in the slope is, or the slope change happens, that's going to be where base flow or groundwater flow in this case is a major contributor to the runoff hydrograph. And on this slide, I added these two figures to help you visualize what interflow might look like. For the figure on the right, I zoomed into a portion of a terrain model, and it might look like what you see on the left. So this picture is taken from the Smoky Mountains, and so we have a pretty steep watershed right here. Here's the ridge line where my mouse is, and you can see how the valley forms, and you have a bunch of little or smaller streams or tributaries that then flow into a larger stream. Again, look at the figure on the right. So there's our terrain model that might depict that same scenario right here. And you can see those red arrows that I drew along that little tributary. And so what those red arrows represent are, well, these could be flow paths for water that infiltrates into the soil. And then within that unsaturated zone of the soil, that water is going to flow down slope. And eventually it's going to reach the stream network. And it's going to exfiltrate or flow back onto the land surface. And then flow within that channel network and move its way throughout the watershed. On this next slide, it's very similar to the previous one, but on this slide I showed, well, this might be a typical flow path for that groundwater flow or that deeper base flow. Here we have the flow path. Water enters into the soil. It's going to flow down gradient or down slope. And instead of flowing into the channel network, it's going to reach the groundwater table and then flow within the groundwater table. And then eventually, at some point in the watershed, we don't know where, but at some point it's going to flow back onto the land surface and in the channel network. So wherever that water table becomes high enough for the groundwater to flow back onto the land surface, that's where that infiltrated water will flow back. And it has, as I had on the previous slide, so inner flow, the residence time or the time it takes for inner flow water to flow back onto the land surface and then reach some point in the watershed, well, it's going to take a little bit longer than surface runoff. Just the process of infiltrating and moving within the soil, it's going to take a little bit longer than water flowing across the land surface. For base flow, it's going to take even longer still. So instead of water flowing a shorter distance and then coming back onto the land surface, our groundwater flow, it's going to travel much further within the soil and within the groundwater table, and then at some point reach the surface stream network. All right, the figure on this slide shows the component editor for a subbasin element. So we have the main tab right here gives us that clue. So we have subbasin. And then we have information about the subbasin area, latitude and longitude coordinates for the centroid of the basin. And then at the bottom of this slide or this figure, you can see, well, these are the options that you can choose from for describing the different hydrologic processes. Base flow is going to be at the bottom of the list. You go down to base flow, you can choose this drop-down arrow right here, and you see a list from among different base flow methods that you can choose in HMS. You can click on an individual subbasin element to open up the component editor to modify or change the base flow method, or you can go to the global change methods tool to change the base flow method for all the selected subbasins. If there are no selected subbasins in the basin model, then the program will automatically change the base flow method for all the subbasins. For entering those parameters or initial conditions for modeling base flow, you could either go to this base flow tab right here where my mouse is at, click on that base flow tab and then define the parameters for the method that's chosen right here. Or you can go to the parameters menu, and once you go to the parameters menu, you can choose base flow, and then you can open up the global editor for that base flow method that you chose. And then you can enter the parameter values and initial conditions for all the subbasins in the basin model using that global editor. I mentioned this before, the base flow methods in HMS are conceptual. So what that really means, and really a take home in this video and then some other videos that we have about base flow modeling, you really need to calibrate the model when using the base flow methods in HMS. And what I mean by calibration is you do need some observed precipitation, observed flow, and use those observations to help you define realistic parameters for those base flow methods. Okay, this last bullet, it has some very important information. It states that the linear reservoir method is the only method to conserve volume. And what that means is losses from the different loss methods, those losses are what is routed to those linear reservoirs in the linear reservoir base flow method. So what you get from that is you get from the precipitation that falls onto the subbasin element, You're going to have excess precipitation goes to the total runoff for the subbasin element, and then losses, the appropriate losses, are then going to be routed through the linear reservoir. You can have different layers, and we'll have a video on that, but it's going to be routed through those linear reservoirs to baseflow at that subbasin outlet. The other baseflow methods, they do not conserve volumes. They're just recession curve options for generating a recession curve on the receding limb of a hydrograph. This last slide shows the types of results that the program will display for you. And for Baseflow, there's only one location that you can go to see the Baseflow results within the basin model map. So whenever you open up a plot for a subbasin element, and that's what you can see on this slide right here. This is a plot for a subbasin element. That's where you're going to be able to see those Baseflow hydrographs. And in this figure at the top, we have precipitation in the upper part of the plot. So there's the precipitation, the basin average precipitation that's falling onto the watershed. And then in the lower plot, we have our observed flow. That's the black line right here. The blue line, that's the total computed flow for this subbasin element. And then the brown dashed line, that is the computed base flow for this subbasin element. And the way that the plot is configured, you can see base flow is a subcomponent of the total computed flow, the blue line right here. If you want to see tabular results, you can also see those for the subbasin element. Whenever you open up a summary table, you're going to see a summary table for a subbasin element. You're going to see different volumes. And so we have the direct runoff volume for the subbasin element. It also displays the base flow volume and then the total volume from the subbasin element. You can also access Baseflow time series from the Results tab. So if you go to the Watershed Explorer's Results tab, you can expand the tree for the different simulation runs. And once you expand the tree for a subbasin element, then you can access those results, which include Baseflow.